name is Christoph Sydora. I'm from the University of Alberta, and I'm a PhD candidate, and my presentation is on a comparative analysis of room generation methods using a rule language-based evaluation in BIM. So, just getting right into the problem, obviously every building goes through some kind of interior design phase at some point, and of course, the goal is to do it as well as possible, right? If you do it poorly, it's going to be uncomfortable, things will be, you'll have problems with accessibility, and in the worst case scenario, you'll have unsafe living spaces. So you want to do it well. But for the everyday person, you're maybe not sure what it means to do, like have a good design. So the kind of rule of thumb is if you follow an expert rules that come from interior design handbooks, then you're good to go as far as having a good layout design. So we're also in the digital age now, where we can use computers for planning and computer design, and BIM, of course, is a big topic here. So that gives us a lot of automation options. So the idea here is, okay, well, if we can do a lot of work on coding the rules from these design books, then we can automate the evaluation of our layouts, and we can determine whether we're doing a good job or not. And then that becomes this cycle of, okay, well, now let's just do minor changes to our designs. Evaluate our changes, do some kind of decision making on those changes, and then you get the cycle. And so that's the kind of general cycle that goes with any generation design methods. So just to kind of look at what's been done previously, so for rule coding, I guess the most typical and I guess the first thing you think of is, well, why don't we just take these codes and turn them into computer executable code, so just coding it out in like C# or something like that. So that's kind of your basic method. There's also a lot of methods out there that are graph-based, where you have your furniture and you kind of connect them through some sort of relationships. And then finally, we have a lot of data-driven methods where you're using probabilistic placement, so just looking at a bunch of examples and seeing what everyone else is doing, and then just kind of mimicking those examples. And there's a lot of different, more complicated versions of creating these heat maps for that as well, so I won't really get into that too much. But what's kind of lacking in all these existing methods? So first of all, you want an easy way to code these rules. So just turning it into, asking an interior designer to write C code is probably not going to happen, right? So it needs to be something that's pretty easy to use. You also want it to be expressive enough to cover the rules, and what I found with the graphs is they don't quite do that, because there's not a lot of logical operations that they have in those graph methods. So they're not quite expressive enough, at least for some of the rules that I've been seeing. And then finally, you don't want methods that are completely data-driven. So if you're using a probabilistic method, then you have to look at a bunch of good designs, or in quotes, good designs. And just because you have two good designs, just merging them together doesn't necessarily mean that you're going to have another good design come out of it. So we don't want something that's completely data-driven. So that's in terms of the evaluation. Now, kind of looking at the other parts, which is the variation and selection. So this is the other moving the items around. There's two kind of schools of thought here. First is, do we just move all objects simultaneously and do some kind of evaluation, or do we put one at a time and move it around? And there's also another consideration, which is, do we want to be more greedy, or do we want to do more exploration early on? So this is these will have effects on how efficient you're going to be searching for your best layout option. So the approach we took is to use a domain-specific language, which I call the rule DSL, which you can see on the right here. And basically, what it comes down to is that it's a lot easier to use than something like a generic programming language. It uses domain-relevant terms that are a lot easier for interior designers to understand, like distance and facing. It's much more expressive than the graphs, because it has a lot of these logical conditioning logic. And it's not completely data-driven, so you are actually giving it rules, and it has to comply to these rules. We're not just mimicking examples. There's just a few other kind of benefits to using a DSL. So in my case, I kind of set it up so that you can swap out a lot of the logical operations for mathematical equivalence. And using that now, instead of having a Boolean true or false or pass or fail, you can have a gradient to search along. And the other thing is that you can infer like a better placement ordering of your objects based on looking at the types within the rules that you give it. So just to look at some previous search methods, or the previous search method. This was one that I did in my master's just as a kind of proof of concept. It was very simple, so we just took a bunch of lines coming out from the walls, from each of the walls, and then each of those points becomes, the intersection of those lines becomes the potential placement locations. And the selection is pretty straightforward. You're just greedily selecting the best location out of all of those. The one that we're proposing here is a little bit more on a continuous search. So again, pretty straightforward. We have our furnishing object that we place. We sample a bunch of points in some radius. We select the best of those, and we just do a greedy selection for this one. And then just repeat the process now with a smaller sampling radius, and then iteratively do that for a number of iterations. And then one other one, so because I kind of mentioned that we want to compare a greedier sampling or a greedier method versus something that's more exploratory, simulated annealing is a pretty common method, and the only difference here between that one and the jump one is that we have some acceptance probability. So it just means that if you're earlier on, you might not accept the best option, and later on that you will kind of commit to being more greedy. So it's a little bit more exploratory, especially earlier on. So there's a few questions of interest now that we want to look at when we're comparing those search methods. First is the efficiency. So if we give a budget to each of these methods of how many checks they're allowed to do or how many rule evaluations they can do on throughout their kind of process, we want to see what the final score will be. So this is just basically how efficient they're going to be. The other thing is how does this perform on different room types. So we have living rooms, kitchens, bedrooms, and bathrooms. And then also want to look at complexity. So if we give it more furnishing and different like room layouts, how does that affect the how high these each of these methods can score or results can score. So I can't exactly go over all of the 8 examples, so I'll just kind of throw one for now. At the bottom, it's the evaluation check count, which is, I guess, the budget of number of checks that each method is allowed to use. And on the side, we can see on the y-axis, we have the final evaluation score as a percentage of, like, it's basically the compliance score for each one. And what you can kind of see is that, first of all, the kind of obvious one is that when you give it more of a budget, they all perform better. Up to a certain point, so they kind of plateau. And that just could be because the rules themselves have some kind of conflicts, or there's just, you can't get 100% compliance. But the other thing to note is that the grid method, for instance, is really dependent on, you know, the grid parameters, the spacing of the lines that you decide. So that kind of has a little bit of a zigzag effect, so it's a lot more or unpredictable depending on the parameters you use. So just to kind of go over all of the advantages of the jump search. So overall, it just gives better results on average, given a reasonable check budget. It has very little reliance on the shape of the room, so you can predict the quality a lot better depending on the budget. So if you have less computing power, you can kind of infer how much that you're going to be receiving or what good quality you're going to be getting out of it. It's a lot more flexible to different challenging layouts. So compared to the grid method, if you give it a different, more complicated room type, it's able to kind of, it performs worse at a lower rate than the grid method would. And then finally, it gives more variation in the final design. So with the grid method, it almost always gives you the exact same layout design because it kind of just selects one point. But this, with the greedy one, because you're sampling, you're getting a little bit of randomness in there, and you're actually getting different designs in the end. So just to give some limitation and future direction. So the simulated annealing and jump search are very similar. The only real difference is one's a little bit more greedy and the other one's more exploratory. And realistically, you could probably have some parameter that kind of guides between the two. Yeah, so that's just kind of a comparison for those. One thing that we didn't really do, which is a very simple kind of extension that would make it a little bit better, would be to just improve the sampling. Because there's no reason that you can't just resample the same one because it's completely random. So just having a better sampling and something like Metropolis Hastings would be a very simple way to improve both the simulated annealing and jump search methods. And then finally, the kind of where we're going with this is we're looking at ways of creating these rules from giving examples, so having a bit of a data-driven approach to it as well, so that you could kind of have an easy way of creating rules given examples. Yeah, so just to kind of summarize the contributions here. First is that we created a jump search that uses a rule language-based evaluation as opposed to the previous methods. And we kind of shown through some of the experiments that its jump search is better suited to the layout generation than the previous grid search and simulated annealing. It just gives better results under different budgets. It's less dependent on parameter tuning from the room scenarios, and it gives more variety in the final layout designs. So yeah, just gonna acknowledge NSERC for funding and University of Alberta. So that's all I got. Thanks.